Okay, this is number 3 on page 534, the word problem, where we have a 12 centimeter by 12 centimeter square, and the midpoints of the sides of the big square are joined to form a smaller square, to inscribe a smaller square inside of it, and so on. Then the midpoints of those are joined to form another inscribed square, and we keep inscribing squares forever, infinitely. And they said, the question asked, what's the perimeter of all those squares? So first of all, let's just start with the big square. The perimeter is 4 side lengths at 12 each, or 48. So we'll just do a few and get a pattern going here. So if that's the case, then that means that, like, from here to here, half a side is 6, and this is 6 from here to here. And so this triangle right here, 6, 6, as a right triangle, is a 45, 45, 90. So we know from 45, 45, 90s, if you have these two sides, then the hypotenuse is 6 root 2. So that means this length across here is 6 root 2. So these sides are each 6 root 2. So the perimeter of the number 2 square in here, the second biggest square, is 4 times 6 root 2, or 24 times the square root of 2. So then I want to look at this square here, and we're hitting midpoints again on this square. So I'm going to look at from here to here again and look at this triangle. From here to here is half of 6 root 2. So that little piece there, from this point to this point, is 3 root 2. And this is also 3 root 2. So again, now I have a 45, 45, 90, where the sides are, the legs are 3 root 2. And so when I multiply that aside by 3 root 2 by root 2, I get 3 times 2, or 6. So that means that this piece here is 6. So the perimeter of this next triangle is 4 times 6, or 24. So that pattern is going to continue, and so on. So let's make a little list of those values, because the first perimeter is 48. So that's like term 1. And then the next one is 24 times the square root of 2. And then the next one is just 24. So they're getting smaller, and so we expect that if the pattern continues, that this is going to converge, this series, to a single sum. So what is the common ratio? The common ratio is, if I take the 24 root 2 and I divide it by the term in front of it, 48, I get root 2 over 2. And you can check that when you multiply this term by root 2 over 2, you will get 24. So that would be the common ratio. And this is definitely less than 1, because the square root of 2 is less than 2. So if the numerator is smaller than the denominator, then that's less than 1. So let's put this into the infinite sum series and find out, if this process continued forever, what that sum of all those perimeters would converge to. So it's the first term of 48 divided by 1 minus the common ratio of root 2 over 2. Now the first thing I'm going to do to simplify this is get the fraction out of here. I'm going to multiply, I'm not really clearing the radicals yet, but I'm going to multiply numerator and denominator by 1 in the form of root 2 over root 2. So in the numerator, I'll have 48 root 2. And in the denominator, using distributive property, I'll have root 2 times 1 minus, so root 2 times root 2 over 2 is 2 over 2, which is 1. Okay, and now I'm going to rationalize the denominator by multiplying this by the conjugate of root 2 plus 1. Whenever I have it in a binomial, the radical, that's what I need to do. So, and I do that, the denominator is going to be the square root of the first term, which is 2, minus the square root of the second term, I'm sorry, the first term squared minus the second term squared, so 2 minus 1, or 1. So the denominator is just a 1. And the numerator is 48 root 2 times root 2. So root 2 times root 2 is 2 times 48 is 96. Plus, and then 48 root 2 times 1 is just 48 root 2. So it looks like the perimeter would be 96 plus 48 times the square root of 2 centimeters. And that's it. And in number 5, we're going to do this, work on the same set of squares, except we're going to compute the areas. And that's it.